Thank you very much. It's a pleasure to be here. My name is Steffen Hoellinger. I'm a field CTO with Confluent, and I'm here today to talk to you about event-driven agents with complex event processing in Apache Flink, which is a truly exciting topic these days because, as you might have heard, there was a recent Gartner study, actually just came out last month in April, that predicted that the average global Fortune 500 enterprise will have more than 150,000 agents by 2028, which is, you might think that might be a lot, but I personally think that number could even be higher, given that everybody in organizations these days seems to be building agents. But funnily enough, only 13% of those organizations currently believe that they have the right AI governance in place to actually govern and orchestrate that additional workforce. And yeah, agent sprawl in that regard is real. So if you think about all these kind of different systems that people use today across the enterprise, all of these systems are building agentic capabilities into their tools. So you will have suddenly a lot of agents living in your HR software, sales software, IT, legal software, marketing, finance, and across all of these different dimensions. And if you think about all these agents having the need to interact with each other, exchange data, and yeah, kind of to some extent work together, this is really something that seems to be a challenge in that regard. And you might think, yeah, orchestration in that sense could be a problem solver for that. So will we have kind of these very smart, universally knowledgeable orchestration agents that talk to the user both internally and externally, and then maybe orchestrate the relevant task to the expert and ideally get the job done in no time at a very high user satisfaction level. But as you might see from this slide, yeah, this already looks a bit complicated. So orchestration, active orchestration, definitely is a strategy that is worthwhile to approach. But if you think about 150,000 agents, this might not be exactly the right tool to orchestrate that many agents. Yeah? So active orchestration is definitely an important subject in that regard. But I just looked at this spaghetti structure of relations and I thought, doesn't this all look too familiar? Haven't we been there before on the data side of things about 10, 15, 20 years ago, looking at people moving data from the operational estate, analytical estate, connecting all their different apps and databases, data warehouses, and you suddenly end up in this data mess that is kind of a huge complex set of ETL pipelines with data fidelity, governance, and latency issues. So what did we use last time to solve this problem? Exactly. Isn't this why Kafka became the dominant technology to move data continuously, specifically from the operational to the analytical state? So kind of one central bus of data in a to move data kind of very reliably at low latency with high guarantees. And it's kind of the same with AI now. So AI systems in that sense really lose context quite easily without data consistency. So this is really the main motivation here to see, okay, how can we actually deliver data very reliably to agents, keep the context intact. Yeah? So it's not so much about latency in that sense for agents in a lot of these use cases. Of course, there might be use cases like fraud detection where you have to have an agent ideally detect the fraud in a matter of milliseconds, but a lot of these use cases are actually latency insensitive, so it's really about consistency. We believe that in that regard, a lot of these AI problems that we currently see are actually just data problems. So think about, there will be a new model kind of coming out every week, yeah, and nobody knows which will be the most performant model according to relevant benchmarks in 3 months from now, yeah. So this is not really a dimension that I think a lot of people can really optimize for. So there was a lot of discussion around fine-tuning and those kind of strategies still 1 or 2 years ago. But at the moment, what I really would recommend most people to do is focus on the data side of things, which is what they actually control, because the data is not changing that quickly as the models will do over the next few years. And the models kind of will be built by the big model builders in the future. So there is almost no reason to compete or even invest a lot of money in fine-tuning. But getting a solid data infrastructure, getting a lot of documentation, ontologies in place, So investing in a metadata layer of data infrastructure is really very important, because this is what I think you will also be able to control in the future, and where the real asset of an organization is today. In that sense, looking at the case of AI, I think batch processing, if you look at how these pipelines currently look like, is just often not good enough anymore in the age of AI. As context gets easily lost, these pipelines are really slow. So if all that you wanted to do is kind of generate a report every 24 hours, this is maybe something you can still get along with. But if you really want to try to serve an agent with the freshest possible context, this is just not going to cut it. Because as you can see here, that agent on this slide is really far removed from where the data originated. So could be, let's say, sensor data that you move directly through a point-to-point integration, which is maybe not the way to go. But also, even if you adopted Kafka here, I think it's easy to see that if you're moving the data, let's say in open table formats to object storage, and then kind of go through a batch processing pipeline, put that data into an operational database to serve that as context to an agent, this pipeline could break in multiple places. It's very hard to govern that properly. It's very hard to keep the context intact, specifically when you're not only looking at an individual event that the agent needs to react to, but maybe as a set of more complex patterns of events that you want to look into. And this is just, I think, a very good example of, in the end, if you start building data products here in the analytical state, very far removed from where the data originated, I think what will happen is you will just build those data products multiple times, because your agents will live in more than one place. And from our perspective, the right way to do this is really to build these data products close to the source and then make them reusable everywhere. And let's look at how we think this could be done in that sense. So one key ingredient here is Apache Flink, which is also the open source technology really at the core of this talk today, which is a very important technology from our perspective in regards to enriching data, routing data, filtering data, joining the data from different streams, or also kind of external databases that you can query and then kind of enrich the event this way. You can standardize the data, making sure that PII is removed, for example, that the schemas are enforced. And in that regard, this is really important to kind of increase the value of the data while it travels through the stream. So Flink is really a key ingredient here, and for a reason became the leading processing engine for streaming in the world at the moment. So Apache Flink originated actually in Germany, here at TU Berlin, so very close from this place actually, and was then continuously developed with Humboldt University and Hasso-Plattner Institute, and it's currently adopted by some of the largest companies in the world. It might be the technology that powers a lot of the world as we know it today, but we are not aware of that. So every time when we, for example, order an Uber, and supply and demand kind of are being matched, what powers this behind the scenes is really Flink. Every single time you buy something online and transact via Stripe, this is a Flink job that is running in the background. Every time you watch a Netflix episode followed a recommendation, there was actually a Flink job running, aggregating the data about your streaming behaviors and then sending the data to a recommendation engine that made a recommendation that was targeted personally for you. In that sense, the Flink job kind of made that experience possible. So looking at these logos, there are a lot of very large companies that adopted Flink for a reason, because it's just the most efficient way of processing large amounts of data continuously in that sense. So this is really also a change in terms of the paradigm of how we compute, because batch in that sense just doesn't cut it anymore for a lot of these use cases, because there's too much data continuously being produced, and then let's say it doesn't really make a lot of sense storing that data somewhere in the data lake and maybe processing it once a day or every few hours. So this is really something where I think when we look at which companies currently adopted Flink already, the common pattern, the common denominator between those companies is they continuously produce a lot of data. So it's the most efficient way to compute in that sense is doing it incrementally, do it continuously. So that is maybe the most important aspect in that regard. Not so much the latency, but really the continuous aspect of computation. Now, where to build all the agents? So this might be the question that you've asked yourself looking at this problem. And yes, there is definitely a need also to build analytical agents. So these are agents that you kind of build in analytical state, kind of on top of where currently, let's say, analytical queries run, where you might have dashboards, where you even train AI or ML models. And then these agents, they can actually be really valuable for these kind of use cases. They're talking to your data, asking questions about the last years of data that then kind of, you take a batch job maybe looking into that data, you take a batch job then to, let's say, train an ML model. Is not something that you do every day, but maybe once or twice a month, yeah, and then you have a better version of your custom ML model, and can actually make use of that. So there is definitely value in this type of agent that people build in the little estate. But there is a second type of agent that I would actually today would like to point your attention to, and these are event-driven agents, and we think they should really be built close to the source. We place them within the data streaming platform, within the operational estate. So this is based on a capability that exists in Flink, that has been added actually a while ago already in Flink 2.1 for event-driven agents to exist, because Flink can actually invoke a model call. So Flink can continuously read from an event stream. In this case, it would be a Kafka topic. And then for each event that comes in, the Flink job can kind of talk to the model. Yeah? And the model in that regard is agnostic, so it can be any kind of model. So you can connect it to, let's say, hosted models in the cloud. You can also kind of, could be a small large language model that even runs locally. So Flink doesn't really care where that model is. It's in that regard really agnostic of the model. It's the principle behind that. So you can continuously for each event say, summarize me, for example, something in the event, or translate a payload of unstructured data into a different language. Classify, so score something, tag something that you really want to do continuously in order to create value. So any kind of generative AI tasks in that sense that you would normally send within a prompt just being done continuously by the Flink job. And then the Flink job has the capability to write again to an output topic. So this is kind of the principle here, that we, in this case can really even fulfill, let's say, the basic definition of an agent this way, and can consider in this example the Flink job to be an agent or to act like an agent. This might be a primitive version, so this is not really a reasoning agent that has several workflow steps. This is something I would recommend not to build this way, but if you want to have something that continuously monitors a pipeline of events, this is a really interesting pattern here. And it can be seen as an agent, which is why we called it streaming agents in that sense. And the only problem with that is it might not be the most efficient thing, not because of the cost of running the Flink job, but because of the, let's say, if you're working with a model provider, this can be very expensive. Think of a high volume event topic with millions of events per hour. Calling every time an LLM for that might actually stretch your budget in a lot of dimensions and be questionable in regards to the return. So what could we do about that? There's actually another category of machine learning that still has value, that people kind of created over the last 20, 30 years before LLMs became a thing, which are traditional ML models. So what you can, of course, also do in Flink is you can just call a traditional ML model. So this is often much more efficient, much faster to run. So one use case would be anomaly detection. So you can basically say, you call a traditional ML model, either one out of the shelf, ARIMA-based statistical models, also multivariate models. There is a wide selection of models being available that you can choose from. There's also some, if you're on Confluent Cloud, there's some models you can just directly start using. But again, as said, Flink is an open source technology, so you can also apply this principle and bring any kind of traditional ML model and invoke that model and kind of filter out anomalies. So this is something that works quite well, also at scale for very large event topics. Then there is one more thing that you can do here. And this is actually kind of at the heart of this talk in regards to how to make this operational, in a way, how to make this cost efficient. So there is one library within Flink that I think personally is the best library. It's also 10 years old. So this was being part of Flink 1.0 in 2016. So it's exactly 10 years old, and it's very reliable in a way that it just uses the state compute capabilities of Flink to continuously compute the state of, for example, a topic according to a pattern recognition function. So you can actually say, for a specific pattern, let's say event A followed by multiple event B's followed by event C, you kind of describe this as a pattern, and then you let Flink CEP, complex event processing, run here to detect this pattern or this sequence of events. And this is just because it's not even ML, yeah, this is very reliable. This is deterministic approach. So it will always find the same patterns, yeah, in the data basically that you search for. You should have a time interval that it searches for, otherwise the memory footprint might be quite large in that sense, but it very reliably will filter out the patterns that you then can put into another Kafka topic here that just contains the relevant patterns, and then you again can make it economical to have a streaming agent, to have an LLM call connected to another Flink job to drive, for example, deterministic actions. So this is really a pattern that you can use, yeah, to kind of circumvent also the ambiguity that is sometimes in these probabilistic LLM approaches, and really get the pipeline here under control in a way that you only filter out the relevant patterns you're interested in and then drive deterministic actions, deterministic outcomes in order to say, this is not an LLM that kind of says maybe 3 times A and 5 times B, but you want to have reliable, deterministic, predictable outcomes that you can drive with a strategy, a blueprint like this to adopt for different use cases. Now, what are use cases in that regard? Here we have an example for pattern recognition with Flink SQL using the match recognize function. So the match recognize function is a function in Flink that invokes basically this Flink CEP library. And you can have here one Flink job written in Flink SQL, just as an example, in order to show how easy it is actually to write these Flink jobs and to make this scalable in that way and also reusable for different types of pipelines. So in this case, what you can see here is it's an example for a stock ticker. So you have a Kafka topic with financial market information. In this case, you can actually use one job to partition by symbol, so you can have as many different financial products in that topic as long as they follow the same schemas to be monitored by one Flink job. You will not need one Flink job per financial product. So this makes it very efficient. Yeah? So it will kind of separately look into each of these symbols. So symbol would be one stock, for example, or one financial product. Then you can define the measures parameter here. Measures is what's being written in the output topic. You can define the pattern, which is here what you see here, this A followed by multiple B followed by a C event. And then you define basically the conditions. So you can basically, in this case, it would be, for example, a price jump going 10 up and 10 down within the interval of 1 hour. So this is very important here to set a useful interval for the relevant use case as a time constraint. Otherwise, the memory footprint of this job might grow very, very large and again, doesn't become so efficient anymore, or it could be kind of expensive, yeah, depending on where you run this Flink job. That would be something that I would take into consideration. Now, what is a good use case for this? Yeah, let's say an example is predictive maintenance. So think you have a factory floor where you have different machines, different sensor data coming in from these machines, and then you have a failure monitoring agent that continuously looks into these sensors and then detects what are the candidates, what are the machines that it thinks they might break soon because the data kind of doesn't look according to the normal duration of the data. For this specific example, you can have a predictive maintenance agent that then invokes a model that, for example, says in which order now should we repair the relevant machines and maintain them. And then you can actually have a human approval workflow built within, like this would be one example of how you could build it, and then schedule the relevant maintenance tasks according to the approved maintenance steps. So in this case, this is just one example of how that could be operationalized, how that could be used. And there is an interesting aspect here. So the aspect is you can kind of build these agents fully decoupled from each other, where you basically say, okay, if you use event-driven architecture here to communicate between these agents, the agents don't really have to know that the other agents exist. So there can actually be as many agents as you want reading into the same topics. And this way you can become, you can have a scalable approach that kind of fully decouples this approach and makes it much more scalable by just applying a principle that we have been using over the last 10, 15 years, which is event-driven architecture. For microservices, you apply the same concept to agents. At the same time, of course, you can also enforce that these agents can communicate with each other. So if you want, of course, you can actually also use something like A2A, agent-to-agent protocol, to actively call another agent. So I think both approaches work, both have their advantages and disadvantages, but I would specifically encourage you to look into event-driven architecture as a way to really make this much more scalable in terms of an alternative communication paradigm that is complementary to direct calls between agents and active orchestration. So you would actually ask maybe why Flink SQL for stream processing? So why not use any of the other Flink APIs, or why not even start Kafka Streams as in kind of a library within Java that you can use also to build stream processing applications? And the answer is there is no reason of why you shouldn't be doing this. Yeah, of course, people are still building Kafka Streams apps today, and it's a great library. There's also a big team within Confluent that is continuously improving it. So Kafka Streams in no means is like a dead project, but Kafka Streams is very much alive, yeah. And I can even encourage you to look into that. Hartmut is a big fan in that regard. So we're looking also very actively in the ecosystem. It is totally valid to build apps in Kafka Streams today. It's complementary to Flink, the way we see Flink, because Flink has different APIs. There is the table API in Flink. There is also the data stream API in Flink that if you're currently on Confluent Platform, for example, the large on-prem implementations, you can actually use the data stream API, fully valid. But I think the main value in that regard that we see for the long tail of Flink is really the codified aspects of Flink SQL. So Flink SQL in that sense is a way of, let's say, if you want to really write 1,000, 2,000, 10,000 Flink jobs, yeah, this is maybe not something that you should do in code, in Java. Yeah? But if you have like one very important job that needs to be very fine-grained, very granular, custom logic in that job, you might not want to use Flink SQL for that, because it would actually end up like with a very complicated, hard to maintain SQL notation. So in this case, I think code is of course superior. So this is why we offer multiple APIs for different use cases. Yeah? And then again, in terms of thinking about the resources of your developers, I think it's really important to say which are the jobs where you should focus on, where you should actually have your most valuable developers have their attention, focus on a specific use case, and this is kind of the use cases you want to tackle with code, where you can have tests and everything. So this is battle tested Java code that can actually have a lot of value there, but there is a long tail. Yeah, there is basically the use case also for maybe hundreds of thousands, millions of Flink jobs, and we currently see that already with some of the large Flink users. They have 50,000 or more Flink jobs, and they're growing 30% year over year. And this is even pre-AI acceleration, so they will soon have hundreds of thousands, not maybe even millions of Flink jobs. And this is just something you should not try to maintain with code, yeah? Because this is much easier to maintain that with a structured, codified notation that, for example, Flink SQL gives you. It's also easier for an AI to generate those jobs. Yeah? So if you think about one of the reasons why you should have schemas in place everywhere, why you should have documentation. So it's actually easier for the agent to kind of continuously generate these jobs wherever the data is needed in a specific shape, size, and form. And then those jobs can actually be created with AI very easily and fulfill the need both for business users and AI to work with data, ideally fully governed. And here are a few more examples of basically how these jobs in Flink SQL could actually look like for different use cases. So this is all, by the way, AI generated. So what we did here is basically we just described risk patterns and basically asked the AI, can you give us a few risk patterns that we can continuously monitor for? And it came up with small and large transactions patterns. So within a 1 hour window, several small transactions followed by a large transaction. This is a relevant Flink job. You can have rapid fire transaction patterns, for example, where you have 5 or more transactions in a 10-minute window, smaller than $10. So this is something where the AI is also very creative, applying existing concepts, established risk patterns, and can actually operationalize this and deploy this as a Flink job very easily. Yeah? So you can actually start creating value from these. And you can actually have several thousands of these Flink jobs at very little cost running continuously. Think of it as it's an additional workforce. Yeah? It's basically continuously monitoring what is going on in your organization. It never gets tired. It never goes on vacation. It doesn't complain. It's the perfect employee, if you ask me, in that sense, but it's very specialized. It does one thing and one thing only. Yeah? It will never really come up with a creative strategy in that sense, but it's very reliable in terms of monitoring what is going on in the organization. Then, for example, here's another example. I mean, we can go on endlessly. Here is monitoring user logins from different IPs, from different countries. And basically, you can always go a bit deeper and maybe even between these different IP addresses determine like if this is, let's say, a user driving from France to Switzerland, or if it's basically two simultaneous logins from different IP addresses that coming from different continents. So you can actually go, of course, here always a level deeper. Here's another use case where you could actually see that you can also actively use AI for this. So think of like, let's say, classical clickstream examples. We have logs that you want to monitor, so you can have a log analysis agent continuously monitoring those logs, for example, with Flink CEP or anomaly detection. And then you can also at the same time have a pattern generation agent that actually continuously comes up with new ideas of new patterns that the organization could continuously monitor. And then you can actually look in your historic data, let's say an iceberg table, where you might have stored, let's say, the events for the last 5 to 10 years. And you can actually see how often specific patterns have been observed in the past. And when those patterns are approved, you can actually say, we add them to the patterns that we continuously look out for in our analysis agent. And ideally, maybe we'll catch, let's say, an outage before it happens. Maybe we can actually prevent a problem for the organization. So this is kind of an AI use case where we really see a lot of potential in to kind of use AI to continuously come up with new ideas, because let's say the bad actors are doing this at the same time. So the bad actors are always like, also today with AI, are testing systems, are basically trying to find new vulnerabilities, are trying to come up with new fraud patterns, for example. So this is kind of a thing where you really have to be on the verge of saying, how can we also use AI to basically be stay one step ahead, or at least try to catch up as much as we can with the bad actors that might exist as well. Then there is another use case that this could be incredibly powerful for, which we think is continuously monitoring ERP data and also continuously monitoring processes. So think of, for example, a use case where you have SAP data, non-SAP data, you join that in a Kafka topic, and then you have operational agents that are continuously looking in that data, kind of knowing when a process deviates from the happy path, knowing when there is a problem in the data. And then there's something that also Flink is really good at in that regard for, let's say, real-time process mining, where you could actually say, we take ERP data and we continuously monitor that. You can actually look for process blockers and SLA violations, because this is something that is normally very hard to do in an event-driven system, kind of looking for events that don't happen. And maybe you have experienced that in case you have been working with event-driven architecture in the past. But in that sense, this is something that's incredibly hard to do, because how do you monitor an event that didn't happen? But Flink is actually really good for that specific purpose, because Flink is kind of a very powerful state computation engine. So you can also do something like a left join. So you can basically say for each clear invoice event that we basically
I joined like 2 minutes ago
didn't see after invoice has been posted within the interval of 7 days, create a new event. So this will kind of very reliably, and again, this is not ML, this is kind of just state computation here, create a new event from this. So you can actually create events from events that didn't happen within your event-driven system. So this is really powerful, specifically when you want to monitor what is going on in an organization. And in that sense, now moving over to the second category of agents, we now saw basically what stream processing and what experiences Flink, for example, can do and can contribute to in the operational estate for these event-driven agents. But what is the role of Kafka and of Flink, let's say, towards all the other agents that you will build in different systems? And I actually think that people will build agents in all kinds of different systems. It's developers building agents in code, using Claude Code, for example, or data scientists building agents on top of Databricks or Snowflake. Salespeople even building agents in Salesforce. Why not? Everybody will build agents to some extent. You can even argue that whoever is not building agents might not have a reason to exist in 5 years from now as an employee of an organization. So all of these people will kind of feel the urge to make themselves more productive, to leverage themselves using agents. So you will have this zoo of agents, this additional workforce that might even be much larger than your existing human workforce as an organization. And the question is really, how do you deliver the best possible data, the freshest context to these agents? And we think that Kafka and Flink, kind of together, can play an important role in this, shaping context as reusable data products that you can then deliver via Kafka to all of these agents. Because Kafka was never really meant as a technology to kind of only have a point-to-point integration. Yeah, there are different solutions to do that, like a message queue. But Kafka's role was always to distribute the data to different systems simultaneously at the same time at rather low latency. So this is a principle that we can actually apply to this, yeah? Because Kafka in that sense is not a silo, it's really the opposite of a silo. It's a data distribution engine that can actually, in this context, fulfill the purpose of delivering fresh context with security, governance, and observability built right within. And this is something that we offer from Confluent's side now as a commercial product as well. So this is the real-time context engine that can be activated as a materialized read-only view for each topic. Yeah? And then you get an MCP server to serve that data to downstream systems. Yeah? At the same time, this is not entirely new. So this is something that actually people have been doing for years. If you think about Kafka streams, yeah, this is a technology and a principle that also in my previous startup we have been applying 6 or 7 years ago. So this is something that is very reliable and works as well. So I would really encourage you, no matter if you're building on any of the vendors with Kafka or if you're basically using open source Kafka, there is no reason why you should not start today basically continuously aggregating context, continuously aggregating data, and bring that data together with AI agents and AI models. And let's say the principle of, let's say you have a Kafka source topic, you can have something like a compacted topic. You can, in Kafka streams, activate interactive queries, which I think is one of the best features within Kafka streams. So you can actually serve a client via a REST API to kind of continuously look into the updated fresh data. So I built myself a use case for conversational data. Based on this principle, it worked incredibly well for years. What really changed now, I think, are the protocols. Yeah, because what you could also do, of course, you could take this context here, this compacted context, sync that into an in-memory database, like for example Redis, and then put up an MCP server and then serve that to an agent. So this is kind of the equivalent of serving a K-Streams application via interactive queries via REST API to an external client. So now what is good context to serve in that regard? I think this is also something that deserves a bit of attention, because here is an example from an SAP medallion architecture where you have bronze, silver, and gold layer. So bronze being really the raw foundational layer where you have like these tables, raw data products where, you know, like if you have one invoice that is spread out over like 15 different tables. And then you actually have the silver layer where you kind of start aggregating this raw data into actual business events that make sense. Yeah. But then you have one level up, this gold layer, where you really have a unified perspective on what is the current inventory situation, for example. And this is really what I think is good context to serve to an agent. So this is also the reason why I think you should actually take out these existing batch pipelines, yeah, where you do the batch processing as a side function in the analytical state, but really move that left. So we call it shift left in terms of what we mean close to the source in that sense, saying, hey, why not continuously aggregate the data for our inventory close to the source in a Flink job, for example. Yeah? And then you can actually serve that as a reusable data product to all these agents that might require this data. So updating the context continuously is not something I think you will get around. This is something that you have to adopt as a new principle in serving agents. Yeah? Because what is the alternative? The alternative is you wait until the agent requires some data to do its job, yeah? And then you kind of get a request. Yeah? And then you might say, okay, now we go off and send a few requests in different places of our data infrastructure. So we query different databases, and then we might reintegrate the results. But if you do this, you have already lost. Yeah? Because how do you recover? How do you basically make sure that the agent can actually get the data at very low latency? So the best and the only way to do this from my perspective is here to do that continuously. So to update the context continuously, so it's always fresh for every agent request. Even if that request never comes, I think it's a different paradigm, it's a different principle behind that. It's also something that if you look what the large model builders currently do, like if you use ChatGPT doesn't wait until you wrote the prompt and then goes off and says, oh, let's look for some memories that might be a good fit. They do that continuously. They basically, of course, have always the freshest possible memory indexed according to different dimensions, so they can actually serve you at very low latency in your usage of, let's say, an agentic chat solution like ChatGPT. But the principle behind it is more universal. Yeah, and it's as soon as you're dealing with a lot of data, that's just the most efficient way of dealing with that data, continuously computing that context, so you're always ready to serve the agent. For example, in a customer support context, but in other use cases as well. So this is something that I would really encourage you to look into. And of course, it's something that needs to be fully governed as well. So it's not only something you should do as an organization, kind of continuously building these agents and serving them with fresh context, but it's also something where governance is an important subject across the entire value chain here of capturing the data, processing the data, and then serving it as context to all of your agents. And there is an interesting aspect, and this is basically the last point I really wanted to convey today, is that kind of Kafka can really fulfill an important role in that sense, because Kafka as an append-only lock has kind of lineage and traceability built within. So it's in that sense future-proof for regulatory requirements that we see coming into existence now around the subject of using agents, because in the future, as an organization, you will not only have to document which models you use. Yeah, this is kind of easy. But it's much more important as well to also document where the data originated from, yeah, and what effect it had in the real world. So you will be obliged to kind of keep the log or keep track of what were the policies, yeah, that, for example, an agent acted at a specific point in time on, where did the data come from that the agent used, which model, of course, was used, which prompts, and also what recommendation did the agent make in order to, let's say, make a recommendation or make an automated decision, decide whether a customer gets a mortgage or not. Yeah, so you can really think a lot about these use cases, but responsibility and governance and security are topics that we have to address in that regard as well. It's not only about who can build 100,000 agents or 1 million agents. It's really about how do you do that in a compliant and in a governed way. And in that sense, I would really encourage you to look at this regulatory environment also as not only a burden, but also an opportunity. Because agent observability, yeah, with Kafka, in that sense, is key, yeah, for compliance, but it's also an ingredient for continuous improvement, because you can take these logs, yeah, and maybe for the very first time, you actually have that visibility into decisions that are made within an organization. Because for human, that's often kind of not accessible. That's often implicit knowledge, yeah, where you don't really have a complete log of why somebody in an organization made a certain decision. So it's hard to kind of interpret. But with the agents, for the very first time, you actually have all these resources, you have all these logs. So you have all this input that you can also use to continuously improve and evaluate and build a better version of your agent. And this is kind of the second message here. What will be required in that sense is a closed feedback loop empowered by the agent's logs to not only build one agent and never touch it again, but to kind of see it as a start of an iterative process where we take in this data and we build the next best version of the agent and the next best version of the agent and continuously improve and act upon of these AI use cases. So thank you very much for your time today. Happy to take any questions if there are any questions. And of course, let's stay in touch and continue to talk about agentic AI use cases that can be powered by Flink and Kafka. Thank you very much.
Okay. Thank you, Steffen.
Are there any questions?
Yes.
I would have one. So at the beginning, you showed this kind of picture where a lot of agents were kind of connected,
yep,
which kind of leads to that agentic mesh idea, right? Where orchestrate the agents would need to discover a lot of other agents. And then you moved into that kind of decoupled choreography-based integration architecture. So what's your personal opinion, or also from Confluent, right? Is A2A really an integration pattern we will see on a large scale? Like I'm not talking about kind of individual workloads, but do we need A to A and agentic meshes in an enterprise-wide integration architecture, or are agents truly kind of choreography event-based and this is the better approach? And last question, do you have reliable insights, right? Not only your personal opinion, but like comparisons, what works, what doesn't, why to go one way or the other one?
Yeah. Yeah, thank you very much for the question. So the question was really around how basically two approaches complement each other, or if there is an alternative, or if there's a better way of doing this. So I think there is actually room for both in that sense. So they're really complementary approaches. And I would actually say active orchestration might be the one that is more approachable in that sense. And of course, there are different protocols. Like there's A2A as just one way of doing it. But of course, agents can be integrated with all kinds of different tools these days. There's MCP. There's also maybe direct calls. There are also people that integrated agents in different ways. But I would really say it's basically using the best of both worlds when the use case is applicable. So I don't think active orchestration will be the way to scale to millions of agents. Yeah. So it needs to be kind of a complementary approach of both sides of things. But I think specifically if you look at the long tail of the use cases, specifically if you think about the I would say the way to scale this beyond a few hundred agents, yeah, so we can argue if it's a few hundred or a few thousand, but I definitely see not millions of agents being actively orchestrated because the overlap will just be too high, yeah. So you kind of need to have like a dictionary of the agents, and you kind of need to have a perfect description, yeah, of kind of what agent is an expert for which domain, and then again, the orchestration agent might lose sight, at some point, yeah, of who's the most competent agent to act. So, of course, there might be different strategies how you could actually solve that as well, like a quorum of agents and other type of strategies in that sense. But I would say it's really something where there is a strong argument of why you need to decouple that and complement that actually with event-driven architecture, so you can have multiple of agents reading into the same topic and then triggering actions. Of course, there might be then again some mechanisms that you need to make sure that they are not counterintuitive actions or like actions that cancel each other out being triggered of this decoupled approach. But I think we also have a lot of patterns already being established in event-driven architecture and microservices over the last 10, 15 years that we can then apply to these problems and then solve this problem on a different dimension.
Okay, thank you, Steffen. So if any more questions, maybe we can connect with you after.
Yes, thank you very much.
Thank you.